Today's topic is taking a look at HVAC. One of the things that I hope to do over the next 45 minutes to an hour is just help the attendees understand the basics of HVAC, some of the terminology and the lingo and the consistency and also the inconsistency for how systems are named and operated. And just thought it might be helpful to others to unpack that information in a webinar. So with that as a kickoff and anticipating that many of the attendees who have joined us today have been with us in the past, but maybe for the handful or so that haven't joined us in the past, just a brief introduction of who I am. So I'm Tom Diliberti, and I'm with Energy Cap. I've been in the energy industry for more than 20 years. The theme of my work and all of my efforts has been to help organizations over the course of these 20 years with their energy conservation initiatives and trying to squeeze out energy savings wherever they can. So spent a lot of time with a lot of different organizations just trying to offer insight and different philosophies and approaches in order to help them become more efficient. And as I mentioned a minute ago, I work with Energy Cap. And Energy Cap, if you're unfamiliar with our tool, is a utility bill energy management software. And so what we do is we help our clients get the utility data organized so they can be utilized for the purposes of energy management. And also some of our clients end up paying their bills directly through our software as well. So with that as a backdrop and jumping in to the webinar today, let's start with the poll question here. So today's emphasis is on HVAC and understanding where there might be opportunities to save in our buildings. So today's poll question is, what's the biggest energy or cost savings opportunity for your organization? And I wanted to list a few here. And so for you in your situation, do you have the best opportunity to save by catching up on some billing mistakes? Or maybe you know in the role that you play with your organization that it's about aligning HVAC runtime with occupancy, where you know systems are running much longer than they need to. Is the challenge you're facing developing an energy conservation culture? Maybe completing retro commissioning projects is something that's on the horizon you know would bring great value. Or maybe it's installing more efficient equipment. Maybe that's really what has to get done. Or maybe there's a sixth choice there. Maybe it's something even that's not on the list, something that you know you're planning that it's going to bring great value to your organization. So it looks like people have responded to the poll here. And let me just give you another 30 seconds to finish. And so let me just end the poll here, but it looks like it's spread pretty evenly. But the two primary things in sharing the results are with aligning HVAC runtime with occupancy and installing more energy efficient equipment. That seems to be biggest on people's lists. Okay, so that's the mindset that we're going into the webinar with. So let's take a look at today's agenda and talk a little bit about where this fits in the big picture. What you see on your screen right now is a roadmap. If you've been with us over the last several webinars, I started the year, and really I guess it was even the end of last year in December of 2025. I provided this roadmap. The idea is I wanted to help others who were planning energy initiatives. I wanted to give them a roadmap or a script, something that they could follow as a way to improve their operations. So the emphasis, the webinar back in December was to go through all the items in this list. And what we've tried to do is to unpack this. So we've had several webinars over the last several months. The first 4 of the year have focused in the blue region. So we had a webinar talking about the foundation of any energy management effort is data. You need to have good utility data. We talked about looking at your 2 utility bills. The last webinar we did was about looking at audits and how audits evolve over the course of time. But today's webinar here in May is we're moving into the purple region where it's automate and optimize. And if you look also at the flow over here, over to the right, the idea is we want to try to keep with you over the course of the year where we can continue to provide information as we go month by month. And hopefully, if you're following along, you can improve your operations. So what I want to talk about today is I want to talk about a lot of different science concepts and acronyms and things that relate back to HVAC. And you can see it's a long agenda today. So I want to start with the basics of heat, talk about human comfort and how complex and hard it is to get people comfortable when you're doing a lot of building management, talk about some of the ASHRAE standards. I want to talk CO2 and humidity, roll through ideas of boilers and air handling units and chillers. and ultimately finish at the end of the presentation with how I think best to control items in order to save energy and ultimately save money. So we got a full agenda, and so I'm going to dive right into the idea of heat. So with this in mind, heat, um, the easiest way to think about heat is its energy. And you either have that energy or you don't. A lot of people, when you talk about HVAC and you think about building management, people talk about occupants being cold or occupants being hot. But I want to make sure you understand there's really no such thing as cold. You either have heat or you don't. And so, by definition, if you don't have heat, in fact, you are cold. But it's important to understand that this concept of heat is the thing that's going to be moving from one place to another. And so if you settle in on the fact that you either have heat or you don't, it's easier to follow it when you're talking about these complex systems and as heat is being transferred from one thing to another. You might also notice here on the right-hand side that there are different heat transfer methods. So this was something you probably learned back in elementary school or middle school, this idea of convection, conduction, and radiation. And so this is how heat is being moved from one place to another. And I also want to give you an analogy that I'm going to return back to several times during today's webinar, and it's this idea of marbles. Because heat is energy, and energy can't directly necessarily be seen, I want to give you something tangible to think about, and those are going to be marbles. So I'm going to talk about marbles moving from one place to another so you can see something. And as we talk about systems and air handling units and chillers and boilers, again, with the idea or the analogy of marbles, hopefully that'll help you better understand how the marbles are maybe getting from inside the building to the outside of the building or vice versa, and through the different systems. Wanted to talk about human comfort as early in this presentation because it's so critical. This is fundamental to building control, and it's much more complex than most people realize. And so let's unpack this idea of human comfort with the things that you can't control, the things that are beyond many people's control, and other factors that affect human comfort. So let's start with the factors that, for the most part, can be controlled in order to keep human beings comfortable. The first is air temperature, and also the easiest. If you've been doing this for a while, I know you're aware that you can change the temperature, control some type of set point in order to establish a temperature in an indoor space to keep people comfortable. Well, you have many times a lot of control over the temperature to set the systems. The second item on the list, though, humidity, many times also you do have some control over humidity, but not as much as temperature, because humidity control many times occurs as a consequence of temperature control. You can many times control air movement or the velocity of air moving through a system. So through the different mechanisms in your control systems, you can ramp up airflow or reduce airflow. But airflow is going to affect people's level of comfort. And so you have to be cognizant of that as you're trying to help people achieve comfort in spaces. And the fourth thing there is mean radiant temperature. So the idea, if you're sitting in front of a window in the wintertime or the summertime, you have the sun coming in that's going to radiate heat, and you might feel the effects of the sun, or you might feel the heat loss by the windows in the middle of the winter time. All of those factors are to some extent within your control as you try to set systems to keep people comfortable. But let's talk about the things that are beyond your control. It's very difficult to control what people wear to work or when they come into your spaces. So the clothing and how well it's insulated can affect people's comfort. Again, hard to control that. People's metabolic rate is another factor that is unique to an individual. The third item here, this psychological adaptation. I wanted to give you this little story to help you understand what this idea and this concept is I, in working with individuals and organizations through the years, have always encouraged those organizations to be very aggressive with building setbacks in the wintertime. And I advocate for a 55-degree setback in those unoccupied spaces in those buildings. And people would always say, wow, 55 degrees is awfully cold to have building temperatures at that level during the dead of winter. And I would say, yeah, you could think about it that way. But I'd also say is, what is the first thing we do, those of us that live in the north and we experience really cold temperatures in the wintertime? The first thing we do during the spring when we have a 55-degree day is we put our shorts on and we go outside and we enjoy the beautiful weather that's outside. And my point for telling that brief story is that our perception of comfort is relative to other factors. And so 55 degrees in the dead of winter could be perceived as pretty warm or pretty cold. And likewise, it's the spring, it's the summer. We adapt to the conditions that we're under. And it's an important variable to understand as you're working with occupants within a building and trying to keep them comfortable. And sometimes you have to highlight the fact that they don't recognize how complex this is and how hard it is to keep people comfortable. And so sharing stories and exposing each of these things really is important to you convincing people you're doing the best you can at trying to keep them comfortable. Some other factors, air quality and acoustics and lighting, all of those things affect ultimately the overall comfort of a person in a space. And so the primary takeaway from this slide is know as you are working in buildings and doing your best to help your organization become more efficient, there are some things you can control and some things you can't. But I think in going through and explaining this to others when appropriate, it helps them to get a better understanding for why this is so challenging and why things change day by day as you're setting the systems. The next thing I wanted to tap into is some standards. There is this organization that hopefully you've heard of before called the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ASHRAE for short. So ASHRAE is an organization that creates these standards. And the first one I want to talk about is a standard for thermal comfort, or ASHRAE 55. So ASHRAE as an organization has established that during the cooling season, most people are comfortable between 73 and 79 degrees Fahrenheit. In the heating season, it's between 68 and 75. And so those temperatures become typically acceptable temperatures to set systems as people manage them throughout the year. The thing that many people don't realize is the third bullet here. The target is that 80% of occupant comfort is satisfaction. Or let me say that in a different way. What ASHRAE is saying is it's nearly impossible to get 100% of the people satisfied in these temperature conditions because of different reasons. Airflow might be different, or it might be the psychology we just talked about, or somebody's metabolic rate, which would prevent them from being comfortable at these temperatures. So what ASHRAE is saying is you have to establish temperatures within this range that you think are reasonable. And if you get some complaints, that's normal. And if you have less than 20% of the people complaining, they would call that a success. So I want to frame it this way, is if you're in the industry of energy management and you're trying to keep people comfortable, you have to set a reasonable bar for yourself. If you try to help everybody become comfortable, if your goal is 100%, you're going to be very frustrated. You have to give yourself a reasonable bar, work within these parameters, and that's just simply the best you can do. And I want to show you in the next couple of slides some other factors that make this even more challenging. But this is where you got to start. You got to start with what the standard is that ASHRAE has provided. ASHRAE also has a ventilation standard. So this is ASHRAE 62. And how ASHRAE defines this standard is they define it based on the occupants within the space or on area or both. And so talking through each of these three bullets, as mechanical teams schedule their systems and they put the values in all of the sensors and the controls in order to manage a system, what ASHRAE 62 says, if you're looking at a people-based airflow, that you should provide 6 cubic feet per minute of air per person in order to have adequate ventilation. So if you're basing your calculations or you're basing your system control by people, it's 5 CFM. If you're basing it on area, what you should do is you should use 0.06 CFM per square foot. Or to do a quick calculation for you, if you had a 1,000 square foot space, and 1,000 square feet is roughly the size of a typical classroom within a school building, what that would mean is you need 1,000 times 0.06, or you would need about 60 CFM per minute or cubic feet per minute of fresh air flowing into that space in order for it to be appropriately ventilated. And ASHRAE also says, really, if you take a look at total ventilation, you should be looking at both of those. You should be taking the people and multiply by the rate, and you should be taking the area and multiplying by the rate in order for you to set your systems to the best of operation and to provide the appropriate amount of ventilation. Now, I know, again, in working with many people across the industry, this is a challenge because the number of people that are in and out of a space changes many days. Square footage doesn't change, no. But you know that every unit of air that you heat or you cool during the different severe weather, the heating and the cooling seasons, you're paying for that air. And so you really want to manage your ventilation and you want to minimize ventilation to make sure people are getting what they need. But you don't want to pay for a lot more air flowing in your building if it's not necessary. The last thing I want to highlight on this slide is ASHRAE also has an energy standard. Sometimes people mistakenly call it ASHRAE 91, but it's actually technically ASHRAE 90.1. But what ASHRAE has done is they've set these standards so organizations can identify efficiency opportunities. And so here you see a couple of things listed like lighting power densities or building envelope, I should say, or equipment performance. So each of these things are identified in ASHRAE 90.1. And I also wanted to make one final thought on this slide about ASHRAE is sometimes people confuse ASHRAE with being a code. So ASHRAE is not an organization that writes building codes. They write standards that some organizations will adopt as codes. So you might have a municipality that adopts ASHRAE 55 and ASHRAE 62 and ASHRAE 90.1 as part of their legal operating code within that ordinance or within that particular jurisdiction. But technically, ASHRAE does not create code. ASHRAE creates standards, and that's why they're referred in this way. Okay, so we talked about human comfort. We talked about ASHRAE a little bit. Let's talk about how complicated this gets. What you see on your screen now is a chart, which I call feels like temperature chart. Some might call this an apparent temperature chart. And using the cursor, I just want you to see over to the left-hand side what we have listed as relative humidity. And across the top, we have air temperature. So what this chart is attempting to show is, and let's just take the top left corner here. If you have an air temperature that's 70 degrees, but it's really, really low humidity, and 10% humidity is ridiculously low. But what the chart is trying to show you is that if you have a temperature and a humidity, those two factors together roll up to indicate how you probably feel. So if you're at 70 degrees Fahrenheit and very low humidity, it probably feels like 65, which means it's going to feel a little bit cool if 70 is typically comfortable for you. But if we stay within this first column, if you take that 70 degrees, now you go to a more normal humidity range of 40 or 50%. Now it feels a lot more like 70 degrees. And then if you, again, stay in that same column on a very high humidity day, 70 degrees can feel very warm, or it can begin to feel warmer at least. It can feel as warm as 72 degrees if the humidity levels are high. So let's just jump in the middle of the table. Let's say it's at 80 degrees and you're at high humidity. An 80-degree day outside with high humidity can feel almost like it's 90 or even more than 90 degrees. So what's the takeaway? What's the point of this? I mentioned a minute ago how energy managers and building control individuals typically have the ability to control the temperature within the space and have some level of control over humidity. But if you lose either one of those, if humidity levels get out of bounds or the temperature level changes, the occupants within the space can feel dramatically different as a result of one of those two changes. And again, the most common is humidity. You might have humidity well controlled within a building one day. The next day, because it's rainy outside, humidity levels outside change. You're ventilating the building a lot. You're pulling a lot of humidity in. And you haven't done anything in the systems to change the temperature settings, but you have a bunch of occupants now that are very uncomfortable because the internal humidity within the building has changed. And the way they perceive it, the way occupants perceive it, is completely different. The takeaway here again is you can only do so much to control the temperature and the humidity within a building and understand outside air and humidity can influence what happens inside a building. And if the phone rings a lot because occupants are uncomfortable, you just have to recognize part of this is the ebb and flow of building management. And so don't overreact to things. Set your standards, use ASHRAE as the guidepost, but know that this is part of the game. And so if you're new to it, this is what you're in for. Wanted to throw up another chart here too, just to make sure that you're aware of this psychometric chart. What you see here, and this is complex, there's lots of lines going across this thing vertically and horizontally and swooping across from left to right. So what this is a plot of, if you haven't seen this before, is it's 8 different variables plotted on one graph. And what this psychometric chart is used for is for moisture management and for engineers to understand how things change within buildings at different humidity levels and different temperature levels. For the purposes of today's webinar, I just wanted to expose people to this if you haven't seen this. But this is an important part of understanding humidity control and moisture management. If you're doing a lot of activities, let's say in the south part of the country where humidity levels are high, Florida would be a great example. You really have to understand the psychometric chart. You have to understand what's called wet bulb temperature and dry bulb temperature. Another word blends into this that you may have heard of is called enthalpy. Enthalpy is a way of looking at humidity and temperature together. And some of the mechanical systems might have enthalpy controls in them. And so my purpose with this was not to teach you all about the psychometric chart. It was more exposure to understand this is the backbone of what's being used for building management when it comes to humidity. Yet another variable that comes into play as we're trying to manage buildings. So in addition to the human comfort and humidity and the things we've talked about so far, the next thing in the list is CO2. So let's talk about what's normal outside and blend back into building control. So the second bullet down here is the ambient CO2 is somewhere in the range, typically between 300 and 400, misspoke, between 300 and 500 parts per million. So if, again, this is new to you, CO2 is everywhere, can't escape from it. CO2 is typically used as a surrogate to understand air quality within buildings. Depending upon if you live in a rural area, you live in an urban area, you live near industry or away from industry, these values can change dramatically from place to place. And as I've said, the ambient CO2 on average is about 400 parts per million if you were to just randomly go to a place in the country. So now how does that play back into building management? So talking about the first bullet now. So indoor CO2 should be about 700 parts per million above outdoor levels. So many times people say 3 to 500 plus 700, it's about 1,000. So when you're managing buildings and your building has the ability to do what's called demand control ventilation, where it opens and closes dampers, lets in more air or less air, depending upon conditions, usually the value that's programmed in is 1,000 parts per million. Now, if you exceed 1,000, you're at 1,200, you're at 1,500, none of that is dangerous, but it simply becomes the standard and what's expected in order to keep air fresh within a building. So CO2 is more diagnostic than it is regulatory, meaning that CO2 is being used to understand the conditions in a building. And I used the word a minute ago, it's a surrogate to understand the quality of air. But what's important about this whole conversation about CO2 is that CO2, the sensors that are used to measure it within buildings, are the number one culprit for what I have seen through my years in the industry of causing building control issues. CO2 sensors get out of calibration relatively quickly. Many organizations don't take the time to recalibrate their sensors, and these sensors are the reason why some mechanical systems run wild. And so, in summary, CO2 is important to understand. We want quality air for the occupants in our spaces. Again, the outside standard's around 400. Usually you want to keep it under 1,000. But the main thing is if your buildings have CO2 monitors, and if the mechanical systems are being controlled at a certain level of CO2, you really have to get in there and understand it to make sure that you are not having waste occur to your buildings as a result of these failing or miscalibrated systems. So let's stay with the theme of ventilation. I have a picture here that I want to go through and some additional terms that I want to explain. So let's start with the picture. You'll see over the course of the next 15 minutes, I'm going to talk about air handling units and a lot of airflow within buildings. And it's difficult to show this because there are so many different variations. I wanted to pick an image that I think was relatively straightforward and easy to understand. And so will this match every scenario? No, it will not. But I think hopefully conceptually you can see the flow of air, how things happen, why things happen. And again, I want to encourage you to ask questions if my explanation isn't clear, if you want to get clarification on something for maybe an issue or a problem that you're dealing with in your own world. So with that in mind, this represents fresh air coming in from an outside into a mechanical system. So these little circles here with the little lines in them, if you are unfamiliar with this picture, these are called dampers. So the typical flow of air into a building is through some inlet where it passes dampers. That fresh air is very likely going to be passing a heating coil or a cooling coil or both. And there's going to be some type of fan that pushes that air into the building. And that's what's shown here on the top. So if you can imagine the air is flowing into a building and eventually that air has to come out of the building. So that return air, again, sometimes is pulled, sometimes is pushed, but the air comes back. And before exiting a building, sometimes there are these recirculation dampers. So there are these little blinds, if you will, for those of you that have just mini blinds at home where you can open and close them. These dampers function in much the same way. So that air that's coming from the space can be ejected from the building and become exhaust air. Or if these dampers change position, it can redirect that air back into the building because maybe the air is already fresh and you had to heat it or cool it. It was in the building and now it's coming back around and you just simply don't want to give it away. You want to re-keep it or keep it back in order to keep the building comfortable. So this flow of air is very common. Again, we're going to talk about several different types of air handling units here shortly. And you'll see there's lots of different words and lots of different terminology, but in general, this is the general flow of air through a building. So let's talk about positive and negative pressure. Buildings can and should be positively pressured. They should be slightly positively pressured. And what I mean by that is the air that's coming in from the outside. There should be a little bit more air flowing into a building than air flowing out of a building. What that does is if you have a little bit more air flowing in than flowing out, keeps the building positively pressurized, and it doesn't allow air to creep in through spaces where you don't want it to creep in from. So let me turn this around and let's say, how about we're putting less air in than air is taken out? In this situation, a building would be negatively pressured. And what that means, if there's more pressure outside the building than inside the building, it means air will be pushed into the building through crevices, under doors, or around windows, and you'll get air intrusion into a building. And many times the air that's pushing into the building is air you don't want to come in. It's either humid, it's hot, it's cold. It doesn't have the quality of air that you want. And so buildings can either be positively or negatively pressured. Most buildings, when they're optimally designed and operated, they have a slight positive pressure, which resists that intrusion of air from the outside. You may have had the experience in your lifetime of walking up to the front door of let's say, a bank or a mall, where you try to pull in the door and the door resists you pulling. Or it actually, the other thing, it could like fly in your face, like it's real easy to pull. Usually pulling in the front door of a building gives you a sense of whether it's positively or negatively pressured. Again, if it kind of comes out real easy, it's positively pressured. If the door kind of sucks in and it wants to resist being pulled out, that is a negatively pressured building. And once again, what you want is you want a building that's slightly positively pressured. So if you are out evaluating your buildings, it's something many times you can observe right away, and you should identify any buildings that are negatively pressured because usually there are other problems associated with it. Last couple of comments on this slide is this is a picture of an exhaust fan. So in addition to an air handling unit pushing air in and taking air out, many times exhaust fans are taking air out of the building. So this device here is not pushing any air into the building. And when systems are well designed and well operated, all of these systems are in coordination with one another, that the right amount of air is being pulled into the building and the right amount of air is being exhausted from the building because the two systems are talking to one another and set in a way that they adjust correctly. And finally, the last thing on this slide regarding building ventilation is something called economizers. Economizers, if you haven't heard this term before, it relates to using in a air handling unit like this, using these dampers, both the outgoing, the incoming dampers, to try to take advantage of fresh air that may be available that would help the building. The best example of this is during shoulder seasons. Many times there's an opportunity to get quote unquote free cooling by using fresh air that's cool outside and pulling it into the building. So rather than turning on some type of device like a chiller or air conditioning system to make cold air, what you do is you take these dampers and you open them up to allow more fresh air to be pulled into the building for the purposes of trying to keep it cool. That's the concept of economizers. So economizers are trying to take advantage of the right kind of air outside. It's not too hot, it's not too cold, it's not too humid. It's the right quality of air outside to be pulled into the building so you don't have to heat it and you don't have to cool it. So the economizers are exactly that. You're trying to get an economy, you're trying to save on the cost of heating and cooling the air because you just already have good quality air outside. Over the course of the first half hour or so of today's webinar, I try to give you a lot of different thoughts. And on this slide, what I want to do is distill that down by industry. So we talked about human comfort and humidity and ventilation. And so if you notice in each of these columns here, is schools are going to operate at usually at different set points than what hospitals might, or office buildings or hotels as you go across here. And without touching on any of these specifically, but just generally saying, you need to be cognizant of this, particularly if you're managing an organization where you have different, maybe you have schools or you have some type of office spaces that need to be managed in one way. You're also in charge of some type of industrial process. So just know that you need to dial in the temperatures that represent what would be comfortable for the occupants in those spaces. Likewise, the unoccupied temperatures, they can vary going across industries as well. A comment about this is I would always encourage you, if your buildings go through periods of occupancy and then lack of occupancy, or where you could be unoccupied, this is usually a great savings opportunity for most organizations is during unoccupied time. And so you notice here that during the heating season, I'm suggesting 60 to 65, but I'd also say you can push the limits on this. This is many times a great place to even be more aggressive if your organization can accommodate that. Something happens to the next row here that we haven't seen yet. We talked a little bit about ventilation, and the 10 to 15 CFM per person is something that's been in the industry for years. And a brief story about this is historically, if you go back 50 years or so, there was a philosophy on building ventilation that changed because of the energy crisis. So what happened, let's say back in the 70s and 80s, is the ventilation standard at the time was I think very low. I guess initially was very high. So the ventilation standard was initially very high. We had the energy crisis occurring in the 70s and 80s, and they squeezed the ventilation standard down from 15 down to 5. What happened at that point is we had thick buildings syndrome come in. So buildings began to show more problems because the ventilation wasn't high enough. And so what happened was the pendulum swung from 5 CFM up to 15. And for the most part today, we've gravitated more towards the building where people feel like maybe the right answer with building ventilation is around 10. But as I described in a previous slide about the ASHRAE code, really it's a matter of how many occupants you have and the overall area of the space. But that's where these numbers come from. The other acronym that you see here is ACH. And so this stands for air exchanges. So what you have in hospitals for patient rooms or operating rooms is you have to have a lot of air exchanges, and this is the big one. So in an operating room, they want to see about 20 air exchanges per hour. And so this acronym is used all the time when you're talking about building ventilation. And depending upon which of the categories, you'll see things described in CFM or you'll see it in ACH, depending upon, like I say, the industry that you're within. This last row here, just talk about the different savings opportunities across industries. So schools, many times it's getting stuff turned off during weekends and holidays. Make sure we're not overventilating. Schools are notorious for having periods of very low occupancy in the evenings where, yes, buildings might be open and there might be students or community groups in a building. But if possible, there's opportunities to reduce ventilation because we just don't have the same number of occupants. And lastly, a really big one, because of the break periods that occur with schools, many times aggressive setbacks are great ways to save for schools. Hospitals, probably the biggest thing to flag here is there are so many unique spaces within hospitals and healthcare facilities. Treating them all the same is a mistake. You really have to understand what type of space you have and what flexibility you have to maybe change and alter the air exchanges per hour, because this really is the game in hospitals and healthcare, is making sure we're minimizing the ventilation to make sure that people are safe and comfortable, but simultaneously trying to minimize the cost of paying to heat or cool air that doesn't need to be paid for. All right, so it's the over ventilation piece. For office buildings, again, the savings opportunity is conditioning empty spaces. If you have parts of a building that aren't used, let's find ways to get those spaces shut down or turned off or minimized. Make sure that you're keeping track of schedules because many times occupancy is dynamic. So you need to have a system in place to manage the schedules. And another common theme is the idea of heating and cooling simultaneously. So office buildings normally have chillers that make cold, boilers that make heat, and those systems can compete with one another. And to some extent, you can't completely stop that from happening, but you can make an effort to minimize it. And that's what I'm saying here as you try to keep people comfortable. Hospitals, I got to tell you, I traveled for many years of my career, and it was not at all uncommon for me to show up to a hotel where a hotel room had clearly been running all day long, super warm or really, really cold when it's late at night. And what I would say is if you manage a hotel space or where there are guest rooms, this I think is the game. It's making sure that you're not heating and cooling spaces where people just aren't in those spaces. We have to allow the occupants of those spaces to control their temperature. And I think it's okay that those spaces don't run when they're not occupied. And lastly, in the industrial category here, again, it's the overventilation beyond safety needs. Certainly, safety is number one, but it's understanding the safety component and relating that back to the cost component. And it's ignoring the process versus the comfort load. So, got to make sure you understand what HVAC do you need to make sure that the process is being completed, whatever that might be in your industrial setting, and then also keeping the people comfortable. So, over this first half hour, 40 minutes of the webinar, really try to unpack all of this information dealing with human comfort and system control. But it all boils down to this is keeping everyone comfortable is really, really tricky. It is very, very hard to manage all of these systems, all the variables, even when everything's working perfect, let alone the real world where you have challenges of things breaking and systems aging and all of the things that happen within an organization. But if I had to give one piece of advice, my Tom tip would be is you have to balance the indoor air quality with energy cost. So understand the things that I've tried to share, how things are supposed to be and what the important standards and parameters are. But no, you've got an advocate in your court. It is really, really tricky and hard to do, but you have to find a way to try to balance those things if you really want to find ways to save money. Okay, taking a deep breath and moving into a new category. I want to start talking again about air handling units. I showed you the picture a few minutes ago about the airflow in and out of a building as a cutaway. And now I want to show you some images and throw some more acronyms at you here, some other industry terms that are real common. So let's start with what are air handling units. So air handling units are exactly as they've described. They are handling air, they're pushing air into a building. And so you're going to be pushing air that's typically heated or cooled, and they all use different amounts of energy, but it changes depending upon the type that you're using. And within a building, you really typically can't change what type of air handling you have. What you need to understand is the benefits. So if you have spaces that share different types of systems, maybe you choose to use one system over another system. So let's start to run through the list. Unit ventilators are typically small little units that are near an outside wall and many times physically connected to an outside wall. So a unit ventilator is something that probably all of us in the call have seen within a classroom. So classrooms are notorious for having unit ventilators. They might be low and flat. They might be vertically standing up within a space. But as I said, they are by an outside wall and they allow air to go through the wall into the space as it's heated and cooled. So unit ventilators are their own category. And the main part that makes them different that I would say is they're just physically many times much smaller than an air handling unit, which is shown here in this picture. So this picture here in the middle of the slide is a typical air handling unit, much, much bigger. It's going to serve much, much bigger spaces. But in general, it's doing the same thing as what a unit ventilator would do. It's simply just going to be physical size. If you take that same air handling unit and now you plop it on the roof, is what you're seeing here. Now it graduates into this category of being a rooftop unit or an RTU. So air handling units can be inside the building, as this picture shows here. They can be on the building. But the things that they typically do is they're going to ventilate, they're going to be pulling air from the outside, they're going to be heating it, cooling, and pushing into the building. You also hear a term called a package unit. A package unit, many times, is literally a package of system that's plopped on the roof. So as a building is made, a crane will put a package on the roof. And what the package unit means is the system itself many times can heat and cool all on its own. It's not getting necessarily chill water from a chiller, or it's not getting, say, hot water from a boiler. those systems within that package unit are able to provide heating and cooling all with the same package. That isn't always the case. And I will also say that many times these acronyms are used and even misused when you're talking to people in the industry. And so if you're new to this and you're trying to figure all of this out, my coaching of you is understand the general principles of what air handling units are and how they function. And don't get caught up with all of the nuances of them because, as I say, even seasoned professionals, I've learned, have used the wrong terms, whether you're talking about an RTU or an AHU or a package unit, but the concepts are all the same. It's you're trying to heat, you're trying to cool, you're trying to ventilate. Few other comments about this is there's a couple systems that make up air or they bring in dedicated outdoor air into a building. So there's an MAU, a makeup air unit, or a DOAS unit. These systems, again, similar to these, but typically what the intent of these systems are not to necessarily heat and cool for comfort, it's to replace air that's been taken out of a building. And the best example I can think of is in a kitchen. Within a kitchen, many times there's a massive exhaust fan that it's pulling a lot of air out of the kitchen. You might have 1,000, 2,000 CFM of air that's being pulled out of the kitchen. These units replace that air with what's called neutral air. So you might have cold outside air that's heated up to a neutral temperature, roughly 68 or 70 degrees. And these systems simply are replacing the air that was pulled out of there. So makeup air units and dedicated outdoor air systems, again, they're typically used in very specific cases. Fan coil units, very similar to unit ventilators. The subtle difference here is fan coil units recirculate air. You will see these inside of a building. Many times they're very small, and all they do is they take and they recirculate air, so they're not ventilating. They're simply taking air and maybe bumping up or bumping down the temperature. You have air handling units. It could be single zone or multi-zone air handling units. What this means is you might have a big box like this, a big air handling unit, and the ductwork that leaves that air handling unit might be a single duct that goes to a single space, and bam, there you have your single zone. Or that duct might split into 3 or 5 different smaller pieces of duct that go into a multi-zone system. So now maybe you're hitting 5 different classrooms or 5 different office spaces, all with the same air that's coming from the same unit. So you can have single zone and multi-zone air handling units. And the last thing on the slide here are what's called variable air volumes, or VAVs and CAVs. So another situation that's possible is you might have an air handling unit that pushes the air out to a space. And at the end of the ductwork, there's this VAV, this box that's in the ceiling many times, which controls the amount of air volume that goes into the space. Let me explain it to you this way. Your air handling unit could create a desirable temperature of air that goes through the ductwork and arrives at your space, and that is how the temperature is maintained. Or you might have air that's created in the air handling unit that flows through a VAV box, and because the VAV box is variable, it changes the amount of airflow into the space. So the way you keep the space comfortable is either by allowing more air in or less air in, and that's how you keep the space comfortable. So variable air volume systems, or VAV systems, are more complex. They have more controls. They are becoming more the standard, particularly in office buildings and spaces that you want them uniquely controlled. And so what I've attempted to do here in the last 5-10 minutes is just take you through all of these different types of systems. And really what I've done is I've just given you the tip of the iceberg. To really appreciate all of these, you really have to unpack them. So you got to get out in the field. You've got to understand, first of all, what are you looking at there? And then talk to people and build an understanding around what's going on. And hopefully what I've done here is give you a good framework to start with. Similar to the air handling units we've talked about so far, I want to talk about a heat recovery ventilator and a few new acronyms here. We have ERVs and HRVs. So here's the idea. These are becoming more common, but it's also one of those systems that I've seen very poorly managed throughout the country. Similar to the other picture we talked about, where you have fresh air coming in from outside. So you have fresh air coming in from outside through this particular unit. And what's happening here, what they're trying to show you in this box, is this air is being heated before it's put inside the building. And how it's getting heated is the air that's already in the building that's warm, the stale air, as it's being removed from the building. In this particular box, it is transferring the heat. So if you pay to heat air and you put it in the building, you don't want to give it away for free. If that particular air already has marbles in it, it already has those heat marbles, as it's passing back through to exit the building, you want to give it a chance to share those marbles and put those heat marbles back into the incoming air. That's what the idea of an energy recovery ventilator is. As I mentioned, these systems, they're becoming more and more prevalent, but they're not very well understood. They're not very well set. And if you're new and you're starting to learn about your buildings, if you have these, the first thing I would check is I would see if they're being utilized at all. Because my experience is many times people take these more sophisticated systems and they turn them off or they disable them because people don't know how to manage them. And so for the purposes of energy conservation and energy efficiency, identify and then start to put solutions together to get them fixed. Switching gears on you now to talk about heat pumps and the refrigeration cycle. No doubt, because of the push for electrification that's happening in our country, you've heard about heat pumps. And heat pumps are just becoming more and more prevalent. I just want to take you through the simple process of the refrigerant cycle and how heat pumps work. And I want to start here in the top right corner. So how a heat pump works is it takes high temperature, high pressure gas. That gas moves through what's called a condenser. And because it's high temperature and high pressure, the condenser allows the heat to be radiated off of this. So many times what you see, a good example of a condenser would be what you have in an air conditioning system at your house, where that heat from inside the house, those marbles, all of that heat that's inside your house, you want to get those marbles outside. So the condenser outside is where that heat gets radiated out. But when you take the heat out of this high temperature, high pressure gas, now it becomes a medium temperature, high pressure liquid. So it has changed phases. So it's gone from a gas to a liquid and it's lost heat in the process. Now you go through an expansion valve. So now what's happening here is you're taking a medium temperature, high pressure liquid, and now you're making it a low temperature, low pressure gas liquid. It's a mix. So this expansion valve is helping you now to change phases and change temperature. So now, if you can imagine, this is cold. So now inside, typically, if you are trying to air condition, you have an evaporator coil. Because this is cold, the heat is going to be transferred to it. And in the process, you're going to get air conditioning. You're going to get cold. Again, those marbles are going to flow in to this, and it's going to warm up, and it's then going to start to push through here, and the whole process is going to continue. So ultimately, what heat pumps are is they are mechanical systems using a refrigeration cycle that simply move the heat from either inside the building to out of the building or out of the building into the building, because heat pumps can be reversed. They can go in both directions. And this is what you see here in this image here. Okay, so this concept of a heat pump is using the refrigeration cycle to transfer heat in and out of buildings, and it's becoming the norm across the country as we try to electrify. Few slides here on boilers and chillers. Here's a few pictures of boilers, and some of the words you'll hear is fire tube boilers, water tube electric boilers. This is the general idea. You make fire in a boiler, and ultimately it heats the water, which gets pumped through a building. So this is a picture of a fire tube boiler. This down here is a steam boiler. And one of the reasons I know it's a steam boiler is hot water boilers will have multiple pipes, and that's what they're trying to show in the image here of pipes going in and out of here. Steam boilers many times don't have those pipes because the steam is being pushed out. There aren't multiple pipes attached to the boiler. And so this here would be an example of a steam boiler, and very robust, just huge, huge steam boiler. And don't forget, water heaters are really just miniature boilers. So the same thing is happening here, where gas typically is burned to make heat. You might have electric water heaters and electric boilers, but they're less common, although becoming more common. But this is a representation for what's the norm. Talking briefly about the condensing and non-condensing boilers. Historically, we've had what are called non-condensing boilers. That was a picture of what you saw on the previous slide. These would be non-condensing boilers, or this one up here. So they require higher operating temperatures, and it's harder for these to be efficient. And if you notice, the efficiency ratings are much lower than for condensing boilers. The image over here is of 4 condensing boilers. And the main takeaway about boilers is we've evolved from non-condensing boilers to condensing boilers. These can be operated at lower temperatures, which means they're way more efficient during the shoulder months. And when you have four of them stacked end to end here, you can stage them on and use more and more of them during the cold time of the year. So the load that occurs in the building can be matched by how you operate your systems. And so, again, this is what it used to be. This is our world formally. And certainly there's a lot of this still out there, but this is what's more common now as people are building new, is using these condensing boilers. Chillers. Chillers, by and large, there are two common things that you see. You will either see with chillers, this picture in the top right-hand corner here is what's called an air-cooled chiller. And what that means is the heat, those marbles that are within a building, they essentially flow out of the building through these fans. So the chiller is going to take all of that heat through the chill water system, and it's going to exhaust it outside through these fans. So this is called an air-cooled chiller. These right here are cooling towers. So this is a water cooling, a water-cooled chiller system. So a chillers ultimately, when they make cold water and that cold water circulates through a building, and this picture here is an example of one. But when they eject the heat from the building, they either reject it through fans or through evaporating water. And so that's what I'm trying to show here in my list of terms. So there's different compressor types, what's called a centrifugal chiller, screw, scroll, reciprocating chillers. So those are the common ones in the industry, and you would pick different versions depending upon the size of your loads and the size of your systems and the square footage you're covering and so on and so forth. And there's also three other specialized chillers. An absorption chiller. What makes an absorption chiller unique is usually absorption chillers are driven by steam. So many times I've seen these in older buildings where it was a steam system from decades ago. The steam essentially is still made even during the summertime when you want to air condition, but that steam energy is converted using the absorption chiller into chill water. So absorption chillers are way less common than these other compressor types over here, but they still exist. And I'm beginning to see a little bit more activity with absorption chillers for data centers. All the heat that's created from a data center, so all of that energy, all those marbles, what you would essentially be doing is collecting them and putting them through an absorption chiller in order to make cool. And a glycol chiller is used in skating rinks. That's the most common application. So it's a lower temperature. And I'm beginning to see more and more magnetic bearing chillers. And so this is just a quick overview of the different types of chillers, water and air cooled, as well as the different compressor types and some of these specialized chillers. Next slide here, just talking about heat exchangers. This idea, there's a picture to the right here of what a heat exchanger looks like in the field. The concept here, though, is you want to transfer heat from one water source to another. And the picture that it's trying to show you here is you have cold that's being introduced next to heat. That's the difference between the blue and the red. But the two different sources of water are not physically being shared. The two sources of water are just able to share the heat, but not the water. The best way I can explain this, if you can picture having two hoses that are intertwined together, and if the hoses were made with a material that would allow the heat that might be in one hose to be shared with the heat from another hose, that's what the concept is in here. Within these boxes, it allows you to have two separate loops of water transfer heat within the box in order to get the marbles out of one and into another for the purposes of heating or cooling a building. And so that's what heat exchangers do within our buildings. As we begin to wind down here, let's just talk control systems. So what I've got on the screen here, just some examples of time clocks. This would be a real simple time clock. I've seen these used before primarily for lighting. So these HVAC control systems becoming less and less common. Most things are digital anymore. This is just a programmable thermostat. And so these may be wireless anymore. And pretty much the standard in the industry anymore is something like this. I just took a screenshot of a computer screen because this is what most building automation systems and building management systems look like. Behind a computer, you have all the switches and levers in order to decide how things are going to operate. And the other thing that they utilize by and large is direct digital control, so DDC. So I wanted to include those acronyms there just to make sure you had exposure to that if you hadn't seen that before. And I think this is kind of my last slide of new material. I wanted to introduce you to this idea of COP and energy efficiency ratio. These are two terms in the industry that are used to describe how efficient a piece of equipment is. So COP, or coefficient of performance, is simply just a fraction in taking a look at how efficient the object is. So typical ranges for heat pumps are between 2 and 5. Air conditioners is 3.5 to 5. But ultimately, it's an indicator of efficiency. And so as you digest information, you say, hey, is that good? Is that bad? This is what you want to look at is what is the COP? And then specifically for air conditioning, there's something called SEER rating or seasonal energy efficiency ratio. And these are very common numbers you hear regarding air conditioning is it's a SEER 8 or it's a SEER 14. The main takeaway here is the higher the number means the more efficient the device is. And pretty much the standard anymore is you're typically in the middle teens. If you have air conditioning units that are, let's say 10, 15, 20 years old, you might have numbers down here, but more and more of these numbers are leaking higher and higher. And so it's a relative comparison of how efficient the equipment is. And again, if you're a newbie, it's just knowing that what those numbers mean and beginning to pick up on the bigger numbers are better. So as we've talked about all of the information in today's webinar, I want to hit back on an approach that I've said many times in my webinars. It's this. My philosophy, and this really comes from Steve Hines, Energy Cap's founder, is if you can't turn something off, then set it back. Your first objective should be to try to be as efficient as possible as let's try to get things turned off. But if you can't do that, set it back. So change the temperatures, manage it differently, and try to achieve savings if you can't get it off. And if you can't set it back, then make sure it's tuned up and that you're running it as efficiently as possible. So there's a lot of things to learn about these systems. There's a lot of different ways to control systems. But if you stay true to this overall approach, you're going to be converging on being as efficient as possible. And as we wind down the last couple slides here, I want to draw your attention to these acronyms. And we had a webinar a few months ago where we had a full acronym list that we provided to people. So this list is available in this presentation here. I tried to put everything in one spot so it was easy to understand. But if you want the full list, because we went through and talked about HVAC, we talked about accounting acronyms, we talked about different categories. I think there were some sustainability acronyms. Please take a look at our previous webinars if it's helpful, because knowing all this alphabet soup is really helpful at the end of the day for really appreciating how these things work and being able to speak as you talk to others. We've got a couple webinars coming up in June. You can see here in another one in July. And Matt, again, if I could pull you in here, I just wanted to give you the opportunity to kind of put a plug in for a Catalyst here coming up in September.
Of course, yes. So Catalyst is our annual conference. This includes workshops, hands-on learning, learning from peers, time to have meetings face-to-face with Energy Cap team members so you can get any help or questions answered that you need. We are currently in early bird pricing, so that ends June 15th, and we will start full event pricing after that. So definitely get it now, the tickets. I can put it in the chat, the link, but save a little money if you are planning to go. You do not want to pay full price.
Love it. Okay. Want to give people a chance if you're new and you would love to learn more about our software, about Energy Cap, please, we'd love to.
Let me get the poll up.
Perfect.
Quick. And we do have some questions.
Fantastic.
Okay. Okay, when that poll is up, I will ask you the first question, if that's okay with you.
Okay. I'm ready.
What year does the ASHRAE standard reference?
Those ASHRAE standards, and I'm just going to toggle back just to others who might be less dialed into the question. Let me just go back to this. So ASHRAE updates their standards every couple years. And so I didn't put the year here. I think the last time they updated their standards was a couple years ago. So ASHRAE as an organization produces a document, and it's the end of the document is appended with the year. because as I say, every couple years, boom, they tweak these standards. Now, these that you see on the screen are for the most part very consistent over time. They've been subtly tweaked. This energy backbone or the energy standard 90.1 will change as the industry changes, but for the most part, the thermal comfort and the ventilation standard, ASHRAE 55 and 62, to the best of my knowledge, have for the most part remain unaltered for quite a while.
And then on the same topic, how do they get access to these standards? Do members of ASHRAE get access to them?
They do. Yeah, what I would encourage, hopefully the person's still on the webinar, but I would encourage go to ASHRAE first, and maybe it makes sense to become a member. But I don't know specifically like whether you would have to become a member to get the information or not. But ultimately, the place to go is go directly to ASHRAE to get what you need. And they're not withholding the information. The organization again establishes these standards, and they really encourage everybody to use them just for consistency.
And the last question is for setbacks on unoccupied set points, do most HVAC turn completely off or mainly just setbacks like airflow and temperatures?
You know what? It's different. I just kind of use this screen as a backdrop here, just looking at this. What we're talking about now is during the heating season. Initially, I mean, we could talk cooling season too, but let's just say we talk heating season and setbacks. For many systems, the way they're designed to operate is, let's suppose you have a setback of 60 degrees Fahrenheit in a school. What that means is if occupied temperatures are 70, students go home, building goes into a shutdown mode or an unoccupied mode. It means the temperatures will coast from that temperature of 70 degrees down to 60 degrees, wherever that set point is, and then the system will sustain itself at that particular temperature. So it won't allow the school to get colder than 60 degrees. And so some systems are more sophisticated and ventilation is turned off during that time because the assumption is the building is empty. So therefore, there's no reason to ventilate. You would just recirculate the air. Other systems don't do that. So as soon as the system engages, it's going to ventilate. And so there's loss with that because you're paying to heat air that there's nobody in the building and you're paying to heat the air. And so my word of advice or my coaching here is understand what your systems do, set these numbers at reasonable numbers. And over time, as you know your systems better, you know your occupancy and how things run, I would encourage you to more aggressively pursue these set points because every couple degrees you can go lower or go higher during cooling season. There's savings associated with that. So go up, step up a little bit at a time or step down a little bit at a time, but there's definitely opportunities there.
Awesome. So those were our questions. I do not see any more coming in, and I know we're a little over, but thank you so much, Tom, for the webinar. Again, everyone, this has been recorded and will be posted to our website either today or tomorrow. But yeah, if you have any questions, connect with Tom on LinkedIn. Feel free to message him. But yeah, thanks for attending.
Thank you, everybody. Appreciate your time. Have a great day. Be safe.
Thanks.